Welcome back. Can I kind of pick up a little bit where I left off? So one of the big breakthroughs in this entire field is the success of a particular class of neural networks, a particular architecture called convolutional neural networks, these CNNs. In some ways, you could walk into this course, just learn about convolutional networks, learn how to code them in Python, and you could then walk out and start a new company. Because these things are ridiculously, sort of unreasonably powerful in their abilities to solve basic, at least computer vision problems, but also many other problems that you can turn into vision problems. If you can turn your, whatever your data might be, it might be genomics data, it might be stock data, if you can figure out a way to turn that into something like an image, and that doesn't have to literally be an image that humans can see, it has to be image-like in that a convolutional neural network can accept it, then you could start asking that convolutional neural network to start classifying it. And so it's as I said, kind of an unreasonably effective architecture. It's been around for some time. Jan LeCun is who's currently at Facebook, was hired there about 5 years ago, is often credited with bringing these to realization, although I think there's some controversy about exactly who found. I think Jürgen Schmidhuber also claims that he invented them, so we'll let those guys fight it out. But similar to other areas of deep learning, the ideas were around a little bit before their time. The principles were there before it was really practical to instantiate these things in hardware. You really needed to get up to speed in terms of the GPUs that you can do the kind of actual computation in order to really make these things effective. But if you come out of this class simply knowing that there's such a thing as convolutional neural networks and you can apply them to lots of problems, you're already a little bit ahead of the game. That's kind of in a nutshell, where the state of the art is. Now, there are certainly other kinds of neural networks, architectures that are very important, that are not captured. There are things like, I think we mentioned yesterday, recurrent neural networks, which we're not really going to cover, but that take in sequential data and take into account that there's relationships over time between stimuli. Convolutional neural networks in their classical form do not take any time into consideration. They only care about space. They only care about relationships amongst pixels. But that's what they're really good at doing, is they're sort of primed in order to take into account the structure that's in space. So if we sort of pick up where we left off yesterday, we were talking about these kinds of neural networks. These are so-called fully connected neural networks. So each one of the input nodes is connected to every single hidden layer node, and then so on and so forth. And in this case, if you're dealing with a fully connected network, there's some computational limitations, because there's a very high number of parameters, right? If this is an image, and so we're not talking about 10 of these, but we're talking about thousands of inputs, and then thousands of hidden nodes across many layers, you have to learn every single one of these weights. And that could be computationally very expensive. That's right. That's the whole goal in machine learning, is basically to, as we saw yesterday, is to kind of reduce the loss by changing those parameters and changing those weights. So lots of parameters equals lots of computation, and that can become forbiddingly large computationally when you're dealing with a fully connected network. So it's computationally expensive to train. So I'm going to take a step back again to talk about this, the abundance of possible spaces of possible images versus actual images that exist in the world. So the good news is that if you go back here, if what you're looking for in a data set is an arbitrary pattern that could be distributed across any number of these input nodes, that's where the combinatorial explosion happens, right? That's where you get this ridiculous, like we think about the images, the number of possible images. Well, what you have to look for is this pixel, over here has a certain value, and this pixel 1,000 pixels away here has a certain value, and some other pixel, in a different location has a certain value. If that's the pattern you're looking for, then it might be almost impossible to find it because there are just so many possible patterns that could occur that are distributed across that very high dimensional space. So that's the problem you're posed with if, in fact, there's an arbitrary set of patterns that you're trying to find. When I say pattern, I mean a pattern that's predictive of something. Like, let's say you're looking for cats and dogs. Let's say you want, right, or a dog and cat classifier. Well, if it's just the case that that images of cats have some arbitrary pixels scattered throughout the image somewhere, and you have to find those, and those can be distributed across any part of the image, that would be a really difficult problem. So the good news is that that's not the case. In fact, the natural world behaves much better than that. It's much more well behaved. The natural world does not distribute information arbitrarily. We're not dealing with white noise images where there's just random pixels, and you have to find the right white noise image, right? The number of possible white noise images is this whole space. That's just too large to search through. Instead, the world contains structure. Things like these kinds of things, edges, oriented edges. And the visual system in humans has been known for some time to take advantage of the fact that there is this kind of structure. So natural images, this is just a nice pretty one that I liked, grayscale, but this is not a random image, right? Clearly not. You could, imagine flipping as many coins as there are pixels, right? And if each time you flip it, that determines whether it's white or black. And, you're not going to get anything that looks like this. What are you going to get? Every single time, pretty much, it's going to just look like confetti. It's going to look like a mess. Well, the natural world has structure. And what we have is a high degree of predictability between one location in an image and a nearby location. And in fact, in this image, you can see it very clearly that there's a lot of correlation between pixels, right? If I choose a pixel here, in almost all cases, the nearby pixel is going to pretty much have the exact same luminance value. So thankfully, the world is not random. If it were, we could never learn on it. It would be impossible. So there's this concept of spatial frequency, which really drives home this idea that the natural world has this kind of order. And this is something that we know that the visual system cares a lot about. So spatial frequency refers to the idea of how quickly things are changing in space. So you're probably all familiar with frequency. Typically, we think of frequency in the time domain. You may think like sound, for example, how quickly the pressure is changing in the air is going to determine the frequency of a sound. Well, how quickly something is the luminous values are changing in an image is referred to as spatial frequency. And as you can see, low spatial frequency is changing more slowly, and higher spatial frequency is changing more quickly. So you can actually see this in this particular image. I don't know if people are familiar with this, but this is actually two different images, one of low spatial frequency and one high spatial frequency superimposed on one another. In fact, we have different channels in our brain for these different spatial frequencies, but you can actually get yourself to see either image. So how many people see? Well, don't say what it is. Yeah, oh, well, okay, who's that? Thank you. Better sit up.
Grandmother. Yeah, but squint, it's you. Oh, God.
Grandmother? Who sees grandma? Albert Einstein? Anybody see Albert Einstein? So now if you just anybody can you
A lot of squinting.
you gotta do a lot of squinting. Okay. You know what I should have done? Here, how about now? Or how about now? Right? And now you can no longer see. So this is now Albert Einstein is basically beyond your resolution because Albert Einstein is portrayed in high spatial frequency. And that's the kind of thing that as you, for example, develop myopia, you become less able to see higher spatial frequencies to resolve these quick changes that are happening across space. The high spatial frequency, by the way, tends to dominate, as you can see. So even though Marilyn Monroe is there, even though maybe you prefer to see her, in fact, you tend to see Albert Einstein. So here's an interesting fact about the world. If you look and if you go out and measure the power spectrum of different, so how much low spatial frequency stuff is out there versus how much high spatial frequency stuff is out there. It's actually a measurable question. And the answer is you get this 1/f² distribution which means there's a very strong tendency. So in other words, as the frequency goes up, the denominator goes up, the power of that spectrum in the actual environment goes down, meaning there are far more lower or higher spatial frequencies. Anybody can do the math? Far more lower spatial frequencies. Lower spatial frequencies tend to dominate. Now, bring that home for me if you can. What does that mean in terms of what we were just talking about? And can you sort of figure out why is low spatial frequency dominant? Yeah.
Most of the background is the low spatial, and we only focus on the stuff that's really.
Well, why is well, it's not a matter of focus. It's literally if you just randomly sample from the natural world, right? This is the natural world. I know it's not very natural in here, but this counts as the natural world. We're talking about real images. So what it really means, it means that there's a lot more slow change than high change, than quick change. So what it really comes down to is that things tend to be, there's a lot of correlation between spatially localized regions. So if you randomly choose a pixel here and a pixel here or a pixel here and a pixel here, they're much more likely to be more similar to each other than different.
I would like to say that we are seeing the world like a horse with blisters, you know?
We're so, well, true. In some sense, this kind of demonstrates that in some sense we're only able to access information at certain spatial frequencies. We have certain channels that are
Just like this.
So is that a high spatial frequency or a low spatial frequency? I'll leave that to you to figure out. Okay, so things don't change much. I guess one way to put, I haven't heard it phrased this way, is the world is kind of boring. Right? Not a lot of action going on, right? Look around, right? And things don't, so where is the action? Well, that's what your brain cares about. And sort of, maybe this is the kind of point you're making. What our brain really ends up doing is throwing away most of the information. We're going to talk about this a little more tomorrow when we talk about the efficient coding hypothesis. The idea that what the brain is really trying to do is encode the critical information, the information that's out there that really matters as efficiently as possible. So what your brain wants to do, in some sense, is to capture the. Sorry, I shouldn't move that. You should put pictures of cats. It's going to capture people's attention. What your brain wants to do, in some sense, and what we want to do, computationally speaking, is take advantage of the fact that it's not arbitrary, that it isn't confetti, and it isn't white noise. That in fact there is structure, and we can ignore much of what's going on and just try to find those points in the image that are informative. And another important point that's going to be really critical for understanding convolutional neural networks is that this kind of structure, this kind of localized structure that we're talking about, the changes, tend to be repeated across images. So if we think about a fully connected network that had to interpret these three different images, it would not be able to encode the fact. There's nothing inherent in that. There is nothing explicit in a fully connected network that will allow it to recognize that this is just the same as this and the same as this translated. These would have to be encoded as completely separate features, because that's what you're doing. You're looking at these pixels, and you're looking at these pixels, and you're looking at these pixels, and you're looking for patterns. So what convolutional neural networks are going to do is take advantage of the fact that, in fact, this kind of localized structure is often repeated, that you have things that are localized, but then their particular location, so in other words, they're locally localized, right? You have this kind of structure that is specifically present here, but it doesn't have to be in this part of the image. It can be in all these different regions of the image. So that's also a very strong motivation for what convolutional networks are going to do. Yes?
It's kind of like saying that in humans, the mouth is generally, it has a relationship to the eyes and the nose and the ears, and that's generic across that classification of a human or a person.
So actually, it's an interesting case. In some ways, the kinds of convolutional networks we're going to talk about, in fact, don't really even take into consideration that the mouth is in some specific relation to the eyes. It's more like saying that we all have mouths, and that's a good feature to encode. Find that feature somewhere on the face. Could be here, up, down, a little bit to the right. Maybe the eyes can be in a different location, but those are good features to encode that there's a person. And they're, even if they're not going to be, and certainly as somebody moves around, right? You don't really want to have a completely separate feature representation for my face when I'm here versus when I'm here, right? You want to encode that sort of as the same thing. And so that's it seems to be a very essential goal, not only of convolutional networks, so as I'm going to point out, in the brain as well. So here's a very, I'm just going to do a real crash course on the visual system, and I mean crash because I'm just going to skip most of it. But there's a couple of different structures in the brain that are, I think, very informative about how computer vision has been, and using deep neural networks has been progressing. So you're taking information to your eyes, and then the eyes, the retinal ganglions. In the retina, there's a neural network, which I'll show you in a second. That neural network then puts an output that goes to the thalamus, which has another neural network in it, and then that thalamus sends its outputs to the cortex, which is the neural network of neural networks. It's that big, giant, folded structure that's the neocortex that's at the most superficial layer of our brain. And that's where all the really cool stuff happens. That's probably where most of learning happens. So what are these different systems doing? So we have these kind of neural networks everywhere. We have a neural network in our retina. And as I said, the retina projects to this lateral geniculate, which is part of the thalamus. And don't worry about the jargon. The point is that there's kind of seems to be different functions to these different portions of the brain, and they map quite nicely to some of the approaches that you're going to learn about. So one way to think about this, so the retina, doesn't really, not much learning happening there. The structure is kind of fixed by the time you're born. And the LGN isn't well understood, so I'm not going to even weigh in on that. But one way to think about what these guys are doing is this form of pre-processing. And pre-processing your data, as Emily will attest to if she's here, that can be half the battle or more in terms of getting your images or whatever your data are into kind of optimized form so that you can allow the neural network to learn. So what kind of pre-processing? Well, this is a response of a retinal ganglion cell. And what they do is they kind of detect differences in an image. So this thing gets excited when, let's see, let me move ahead a little bit. Whenever there's a change between light and dark, oh, there it is. So it gets quiet when there's dark in the middle. It only likes it when there's light in the middle, and then dark on the outside is what it really responds to. So you don't get that big popping when it's a little too quick, but you can see it. Right, when there's a black in the middle and light on the outside. So this is something called an on-center, center surround receptive field. It's a cell that responds specifically when there's a bright spot somewhere surrounded by darkness. And so what retinal ganglion cells are really doing are looking for changes in the image, right? So I mentioned before, right, we got the 1/f and the boring images. We don't really care about when things aren't changing. We care about when things are changing. Because if you're able to predict the value from one location to the next, then there's not really much point of encoding all of those different values. You can essentially throw them away. You just need to know what's happening at the point of change. And so one of the pre-processing steps that are often taken in relation to images is to do this kind of decorrelation. So this data is very correlated, right? The value of this on this axis predicts quite well what the value on this axis is going to be. Well, what does that mean? Let's think about in terms of images. What are the dimensions in an image? Quick pop quiz. When we talk about the dimensions in an image, what does that mean? Anybody remember? Like think about the axes of an image. Anybody? Why is an image a high dimensional? Yeah.
You have RGB, so you have 3 colors, and you have the values from minimum to maximum, that range, and that's basically.
Okay, well, but it's much worse than that. It's not the 3 values. It's the pixels themselves, right? Each individual pixel, again, so one way to think about it is if you had a white noise image and you had to send that over the internet or tell your friend what's in the image, what would you have to tell them? You'd have to tell them every single pixel value. You'd have to basically specify. So that's how long your vector would be. If you have to write down that image, you have to write down every single value. And so they're high dimensional because basically the axes of an image are each pixel. And one way to think about what's going on in real images is that they're very correlated. Many of those pixels are strongly correlated. If this axis was the value of, this pixel, right, and this axis was the value of the pixel right next to it, then you would find across lots of images, those would be very strongly correlated. One would be predictive of the other, right? The value in this pixel is going to be very correlated with this pixel. And so what you want to do is decorrelate your data. Now, this is not the best example of this because what you really want to do is decorrelate to the point where you can ignore most of your axes. You want to throw them away. We're going to talk about dimensionality reduction tomorrow in a little bit more detail. But if you just look for edges, so this is whitened data. We won't get into the whitening too much, except to say that the lateral geniculate kind of does it. And what whitening does is it makes sure that no particular axis or no particular pixel is privileged. It's sort of equally represented in your data. So this is whitened data, and this is something we typically do. And we'll whiten our data before what this does. If you think of gray as 0, which basically means you're not going to respond to it, you're not going to, you could, in some senses, kind of throw away that information, then what's being really represented here are things like edges. And that really dramatically reduces the dimensionality of your data, and it allows you to capture the structure that's in there. So if we start looking at what kind of structure, so this, we don't care about this structure because that's boring. We care about this kind of structure. Well, what do we see? We see these kinds of oriented edges. And those are the kinds of things that our brain actually encodes. And so as we get into higher levels of the brain, what we'll start to see is not only localized structure being encoded in a specific location in space, but we're looking for features that occur in different locations. And as we get further along in cortex, you actually see this kind of location invariance. So I mentioned like the cat. Well, if you have a neuron that responds to something like an oriented edge, or maybe something as complex as a cat, you want it to respond wherever that object is, wherever that feature lives. So real quick, I know we're just going to go through each one of these. Yeah, right. At the end of the course, you'll be asked to fill in different. So this is the visual system. This is the visual cortex. After we've done our pre-processing, information is sent to this region here in the back of your head called V1, primary visual cortex. And then from there, it projects to, so that's to your V1, and then it projects to lots of different areas. So this is a very, very rich, dense, complex, our neural network, right? This is our biological neural network.
And from there to the first ganglion, cervical ganglion, and from there to the pineal gland.
To the pineal gland? Yeah, I can't speak to the pineal gland. It doesn't make it onto this chart. As far as I'm concerned, it doesn't exist. I'm kidding, but there's enough of these, right? There's enough visual areas. So vision is really hard, right? We saw the guy where you can't tell the difference between the guy, when the change blindness example. Our brain is doing a lot of hard work. It just doesn't tell us that it's doing this. So what's going on in the cortex? First of all, this is where learning happens, right? This is where you see this is where you get dramatic changes in structure depending on your developmental experience. For example, somebody who's blind will not lose their occipital lobe, but it'll take on a very different structure. It'll encode different kinds of sensory information, like tactile and auditory information. So these the kind of structures that we find in cortex are learned. And so in a nutshell, one thing we can say about the cortex is that you see this increase in complexity as you go deeper into the cortex. So if we think about our neural networks, right, we're talking about the hidden layers. So as you get further along in those hidden layers, if you measure the responses, so just the kind of experiments we were looking at before, you take an electrode and you measure its response as you show it different stimuli, you'll find that you get increasing complexity as you go further along. This is going to be a very important feature also of our convolutional neural networks. What they're doing, in some sense, is first you measure features, things like oriented edges, and then you take features of features, right? We can think of them as patterns of patterns, right? Looking for this kind of pattern. And then if you aggregate patterns like these, you can turn them into more complex patterns and so on and so forth. So primary visual cortex, which I just mentioned, that's the first stop after the thalamus ends up in the cortex. You see these responses to these oriented edges. These are called gabors, which are mathematically defined, and long before anybody knew that these were in the brain. They were kind of mathematically defined as being a very useful way of encoding information because they're frequency and space localized, right? They have a particular frequency. You can see that this can change faster or slower, and it also is spatially localized in an image. This is anybody in computer science or does image processing might recognize these as basically wavelets, which was a big improvement in image compression technology. And so it's basically using the same technology that we now know the brain does as well. So if you measure V1 neurons, they seem to optimally respond to these kinds of features. So these are simple, localized, spatially and frequency localized features. And then as you get further along, you get these higher level features. So let's skip all the way to maybe some of the highest levels of processing. We get things like a face area. So these are neurons that respond specifically to faces. Although there's some controversy around that, but I'm going to keep it simple. They certainly respond, in most people, they respond optimally, or most to faces. And so what's happening here is, as I said, is you're starting off with simple features, and you aggregate and combine those features into more complex features, and then you can get something that's really extremely specific. And there's some interesting phenomena that it seems quite clear that this part of the brain is kind of selectively responding to this important ecologically and sort of socially important kind of stimulus. So this is just one of many examples of the fact that face processing is unusual. It's different than other kinds of processing. So I don't know if you've seen this before, but these two faces probably look pretty similar to each other. But that's because they're not the pattern that your brain is looking for. This isn't really going to activate or strongly activate that part of your brain, those neurons that are looking for face-like features. But if you flip it over, same images, right? So now you can see it. So which one is it, right? It's actually this one here. That's weird. It's even hard to tell. But this activates those neurons that have been conditioned or trained, right? We've trained our neural network, that is our brain, to be particularly sensitive to certain patterns that are face-like, and that once you activate those, now you can detect when there's something is amiss. And this gets even crazier on some level. So there was a very well-known study in 2005 where there was a patient who's because they had open brain surgery, and they were measuring single-cell responses deep in, this is actually hippocampal, and they found neurons that responded not just to faces, but to specific faces, namely the Halle Berry neuron, and also there's a Jennifer Aniston neuron. Right? And each of us has one of those. Now, as William mentioned yesterday, nobody takes seriously the idea that there's a single neuron. There's a grandmother cell that is wired up, in a very simplistic way, looking for one specific person or one particular kind of pattern. Almost certainly, there's a distribution. We'll talk a little about it more tomorrow. There's sparse code that there's a population of neurons that are probably pretty well distributed that probably encode the presence of Halle Berry. But that being said, you do get this there certainly is a high degree of specialization that happens further along. One way to think about this is the further up you get in visual processing, the more picky the neurons get. Photoreceptors, they're really just, they'll hang out with anybody. They're very promiscuous, right? Any light, right? Any degree of light, they're going to basically respond at some level. And then as you get to V1 or even LGN, or I'm sorry, even retinal ganglion, right? The last layer in the retina, they become more picky, right? They're looking for edges, and then you're looking for oriented edges, and then you're looking for things as complex as faces and even specific individuals.
By the way, the Halle Berry cell refused to respond to Brad Pitt.
They tried though, huh? Don't tell him that. You probably read the paper. Anyway, so one important point is that as we get further along in these higher layers, we get receptive field size increases, What does that mean? Well, what that means is that you can get the same feature. So a feature that drives a neuron, let's say it's a particular face, you can move it over a bit. Locally, it doesn't have to be spatially localized. That's not true for V1 neurons, which are really, really coupled to a very specific location. Actually, that's not quite accurate either. There are complex cells, even in V1, that show some invariance, as it's called, so invariance to location. So you can move the object. The feature has to be right, but its location doesn't have to be precise. And so, again, this is going to be an important point when we get to convolutional neural networks. And one last point about the brain, and I'll get out of the way, is that this is not just true for the idea of this interconnected higher level features that integrate information from the lower level features is not just true of the visual cortex. It's true in other cortices as well. And in fact, what we see is that there's integration of information. We can think of the brain as, well, a giant neural network that integrates information not just from any single modality, but from across multiple modalities. Somebody asked the question, I don't remember who it was you, Craig, I think, about, what about if you have, you're measuring information from sound and you're measuring information from vision. You got images and you got sounds. Do you train two different networks and then combine them, or do you train a single neural network? And there's ways to do that. You can turn those both into vectors, and you can sort of concatenate them. Here's my vector that's describing the visual information. Here's my vector describing auditory information. You can feed that into a single neural network. That's what the brain does. Right? The brain really takes in this information, then it actually combines it all in that thalamus, and it really does treat it as a single single input. And we can see this in these kind of really cool audio-visual effects. Has anybody not seen this? People familiar with? Oh, good. That's fun. Okay, so this is called the McGurk effect. If you watch this person, oops, did I put on that music? No, that's somebody's phone. Okay, so what did he say?
Hang on, play it one more time.
Okay, right, here we go.
Put it full screen. So
Good call, good call. That is a big, shaggy face. Okay, so maybe you heard something. It's a little bit hard to make out, probably, but maybe something along the lines of a da. People hear da? Ga. Who heard ba? Okay, so some of you heard ba. Now you'll all hear ba. So here's what you do. Just close your eyes and I'm gonna play the same thing, or just look away from the screen. Just make sure you don't see it at all, because if you see it at your periphery, it's gonna change it. Now what do you hear? Right, now you can get it to switch midway, right? You can actually, right? It'll actually change on you. So what's going on there is, well, this is, in a nutshell, this is actually a recording of somebody saying ba, an audio recording of somebody saying ba, a visual recording of somebody saying ga, and what your brain is doing is it's integrating those. So it's getting features that are consistent with, that's consistent with ba in terms of the auditory, and it's getting features that are consistent with ga in terms of visual, and at the output of this thing, it's converging those. It's clear that that are sort of behavioral output or sensory output. I'm sorry, our perceptual output, right? The thing that we actually hear in the end is integrating these different sources of information. So this is, in some ways, in a nutshell, what the deepest and broadest approach to artificial neural networks is going to entail. Basically, throw all the data in, right? In some ways, this field of deep learning can allow you to be kind of stupid about how you think about your data. You might want to do pre-processing to get things to be somewhat optimal, and you might want to draw inspiration from the brain. But at the end of the day, we really want to engage in what we'll often refer to as end-to-end learning. Just throw the data in there, tell the system what the class is, and let it sort it out, what's important. Let it sort out how to integrate the various different sources of information. And because you never learned to do that. Nobody instructed you to read lips, right? You never learned to do that. Nobody instructed you what a certain sound, a phonemic sound of ba versus ga. You didn't actually have to sit there and learn. Instead, you just experienced it. And you learned that there's a meaningful distinction between ba and ga, because our language supports that. Other languages, by the way, which don't support a big difference between ba and va, for example, if your primary language is Spanish, you might have difficulty with your bas and vas. And so our brains sort this out. And so that's sort of the magic of these networks, is that all of this integration and all this feature learning just happens through some basic principles. So we're going to talk about some of those principles next. I think we're going to take a quick break before you go, because we still have to figure out the EV or not.